physicist and I build quantum computers for a living, I frequently get one of two responses. The first is a blank stare. The person has no idea what the word quantum means. And the second is that they get really excited, which is awesome. But then they'll ask me when I'm going to solve quantum gravity or how they can use the computer to mine for Bitcoin. Just so we're on the same page, neither of those things is possible right now. So this is something I've struggled with on and off again for the last few years. I really want to be able to explain what I do to people in a way that, does justice to how exciting this field is, but also tempers that with a little bit of realism in terms of, what is possible and what isn't with the quantum computer. So that's what I'm hoping to get to today. I'd like to talk a little bit about quantum computing and why you should care about it. And then I want to tell you a little bit about what processors that we have available today are capable of and where that might take us in the next 1 or 2 or 5 years. So to talk about quantum computing, we obviously have to start with classical computing. So I use the word classical to refer to the technology that we have currently available. And all of the processors that are in our laptops, our cell phones, some of our watches, are all based on a technology called the transistor, which has been around since about 1947. So the transistor is just a simple electrical circuit element, which acts a little bit like a switch, so it can be on or off. In computing or information processing, we usually talk about the transistor being a bit. So a bit is a single piece of information, so it can be 0 or 1. So what I have behind me is a plot of something called Moore's Law, which was more of an observation and a self-fulfilling prediction made by Gordon Moore in the 70s. And basically what he saw was that every 2 years, the number of transistors on a processor chip tends to double. And this corresponds to a doubling in our computational power. So you can see that that's held up quite well over the last 45 years or so. We've gone from about 1,000 transistors on a chip to almost 20 billion. But it's important to know that the way that we've made these improvements is by scaling down the physical size of the transistor. So we've shrunk it and shrunk it and shrunk it and shrunk it, and you can imagine at some point we just can't shrink it any further. And it turns out that that time is coming up pretty quickly. The processor in your laptop, for example, the transistors there are about 20 to 50 atoms across. So they're really, really small. So if we want to do better, we need to look to new technologies. And you might say, hold on, we have so many computers everywhere. You just told us they're in our watches. And we have access to more information faster than we've ever had before. Do we really need to do better? Is this not good enough? And I would say, yes, we absolutely need to do better. Because even as the scale of humanity has grown, as we've become more interconnected, the size and scale of the problems and the complexity of the problems that we want to solve has also become much larger. And I'm not really talking about math problems here, although those are also very important. I'm really talking about real-world problems that we as a society face today. So let's take the healthcare industry, for example. Most of us are aware there are a number of diseases that we don't really know how to cure or even treat effectively right now. And how would we go about trying to treat these? Well, in a lot of cases, we do a drug trial. We try a new chemical compound and we see how that works. But before we do a drug trial, we want to be pretty sure this drug is going to work, because drug trials are really expensive, not just financially, but we don't want to risk people's lives. And it turns out that that problem is very difficult, figuring out what drugs might work. And that's something that a computer could help us with. But the space of molecules that we could explore is just far bigger than what we can do on classical resources that are available today. So my proposition is that quantum computing is a new paradigm, a new tool that could help us solve these problems that we just can't attack right now. Okay, so how does it work? I'm not going to pretend that I can explain all of quantum mechanics in 10 minutes. That's just nuts. But I want to give you a little bit of a sense of how that works. So basically, quantum mechanics is the physics of very small objects, and it leads to some very counterintuitive things, and that's just because it's not what we experience in our everyday lives. So for example, if I take a ball and I throw it to the back of the room, I can more or less estimate where it's going to land based on the angle that I throw it at, how much force I put behind that. If I'm outside, maybe the wind speed has an effect on that. But if I shrink the ball down to the size of an electron or an atom, that's no longer the case. So let's take a look at that. So I'm going to tell you a little bit about a few of the funny things that happen when quantum mechanics comes into play. So for all of these examples, I'm going to use the analogy of a ball. So if I have a classical ball, I'm going to tell you that it can be a red ball or it can be a blue ball. But it can't be both, and those are the only two colors it can be. It cannot be any other color. If I make this ball quantum, that's no longer the case. My quantum ball can be red, or it can be blue, or it can be red and blue at the same time. I've drawn this as half red, half blue. That's not really an accurate representation, so you'll just have to trust me that it's actually red and blue at the same time. Okay, so this is something that comes into play. It's a little weird, but we call it superposition. So we say the quantum object is in a superposition of the red and the blue at the same time. So that's pretty cool. It turns out to be very useful. But what happens if I try to look at this quantum ball? Well, it turns out that I, as a classical observer, cannot actually view this superposition. The very act of me trying to look at the ball forces it to be either red or blue. Okay, let's move on. What happens if I take two of these quantum balls and I put them in a special kind of superposition state that I'm going to call it an entangled state? Well, this leads to some very strong correlations between the two balls, so strong in fact that it no longer makes sense to talk about them as separate objects. We actually call them inseparable. Okay, so that's a little weird. Let's try to understand what's going on. I told you that if I look at this superposition ball, I should see one of the colors. So let's do that. Let's assume I look at the first ball and I see red. Well, without looking at the second ball, I immediately know that it also has to be red. Conversely, if I look at the first ball and I see that it's blue, the second one must also be blue. And this is what this entanglement is about. Now you might think, okay, well, these two balls, clearly they interact in some special way. What you're doing is you're looking at the first ball, and the first ball is blue, and it's saying, communicating to its partner, like, I'm blue, you gotta be blue too. And you'd be, that's a reasonable thing to think. Many physicists actually did think that's what was going on, but it turns out that it's not. And I can prove that because I can put these two balls on separate rockets and send them to either end of the universe. So far apart that there's no possible way they can communicate with one another. And it turns out that if I have an observer on one side of the universe with the first ball, and this person looks at this ball and sees that it's blue, immediately the second person with the second ball is going to see that the other ball is blue as well. So that we have these very strong correlations that persist across very large distances. The third thing I want to talk about is what happens if I put a mountain in the way of my ball. So in the classical world, if I have a ball and I have a mountain, the only way for that ball to get to the other side of the mountain is to climb up over it. So that means it has to have enough energy to get to the top of the mountain first before it can get to the other side. If it doesn't have enough energy, then it's stuck. That's it. It just can't go anywhere. In the quantum world, it turns out, yeah, that's not a problem. The ball can't be inside the mountain, but it can just tunnel right through it. And that's called quantum tunneling. It's kind of a weird thing that happens. Okay, so here's some weird stuff that happens in quantum mechanics. Hopefully you guys are like, oh, this is weird, but kind of cool. What does that have to do with computing? Okay, so let's talk through them one at a time. So superposition. Okay, if I have a classical bit, I have a transistor. It can be 0 or it can be 1. If I now make this bit quantum, or qubits, it can be 0, or it can be 1, or it can be in this superposition state where it's 0 and 1 at the same time. Now what that means is that, in a classical processor where I'd have to explore the 0 state and then the 1 state for all the different qubits kind of one at a time, with a qubit, it's actually sampling both states at the same time. So we're looking at potentially a massive speed up in the computational speed. The second one, entanglement. This basically means that I can send two qubits really far apart and they will still kind of hold their correlations. So this is really useful for transferring information, and particularly quantum information, across very large distances. The third one, tunneling, let's think about, if we're trying to solve a problem. And I'm going to say, on one side of the mountain is a space of pretty good solutions, but maybe not the best ones. And on the other side are much better solutions. If I have a classical processor, to get to those better solutions, it needs to have enough energy to get over the mountain. If I have a quantum processor, yeah, it turns out that's not really so much of an issue. The quantum processor can just quantum tunnel through this mountain and get to the better solutions. So that's the way that this can help us with computation. I am not going to talk at all about how we build a quantum computer, because there are many, many, many ways to do that, and there are many, many research groups and companies around the world working to do that. But we do have a couple of quantum processors available today. So what I want to ask is, what can we do with them? And I'm going to give you 3 different examples of problems that we can start to tackle with the processors that are available today. The first one is material science. So these two kind of pictures are depicting 2 different simulations of basically crystal lattices in 3 dimensions and 2 dimensions. And in both cases, the researchers were looking for something called a phase transition. So phase transitions exist all around us in nature, but a very simple one that most of us understand is solid ice melting to liquid water. That's a change in state, and that's a phase transition. In this case, these researchers were looking for quantum phase transitions, but it's a similar sort of idea. The work on the right is particularly interesting to me because it reproduced something called the Kosterlitz-Thouless phase transition, which is something that happens in magnetic materials at 2 dimensions. Don't worry too much about the details. But it was the subject of the 2016 Nobel Prize in Physics. So it's pretty cool that we can now actually simulate that Nobel Prize winning work, on a quantum processor. And you might look at this and say, okay, cool. For basic science, yeah, maybe this is interesting, but how does this ever have an effect on my real life? And the answer is, right now, probably not much. But as we scale up the size of the processors and their power, we can start to think about scaling up the size of these materials and actually using the quantum processors for investigations of new materials. So we could think of things like, new shielding materials for spacecraft, or maybe biodegradable polymers, as a couple of examples. Okay, so let's look at this, materials simulation, which is kind of a full crystal lattice, and let's think about scaling down what we're actually looking at. So instead of looking at a full crystal, let's just look at a molecule. So it turns out we can do this too with a quantum processor. So behind me are 3 kind of graphs, and what we're looking at is the potential energy as a function of the distance between 2 atoms in the molecule, and we have 3 different molecules. So there's the H2 molecule, the lithium hydride molecule, and the beryllium hydride molecule, kind of the 3 simplest molecules that we know of. What I want you to notice about these graphs is that the black points are data taken from a quantum processor, and the dashed colored lines are what we know to be the exact solutions to these molecule problems. So you can see that, they're small molecules. Clearly, if we already have an exact solution, the quantum processor is not really adding anything at this point. But what's important to note is that the quantum processor is starting to get pretty close to what we know to be the right solution, and that as we can, again, scale up these quantum processors and scale up how efficient they are, we can start to expand the size of these molecules, so we can make them much larger, and this is directly getting at that very first problem I talked about, which is new drug discovery. So this is how we would figure out what drugs should we be trying. We do simulations like this. Okay, so the last application that I want to talk about is kind of my favorite, because it turns out that quantum processors are actually very well suited for these types of problems. So this is work that was done by Volkswagen over the last couple of years. And what they looked at was the distribution of taxis along a certain route. So behind me is a map of Beijing. And what you're seeing is the route that taxis in Beijing are taking from the center of the city to the airport. And you can see that they're all pretty much taking the same route, which is causing a lot of congestion. That's those red areas. And so everybody's late for their flights. So Volkswagen, took this to a quantum processor and said, how can we optimize the routes of all of these taxis as a collective, group, such that people get to the airport in the least amount of time as a whole. So they put that on a quantum processor, and they came up with a map that looks a little bit like this. It's much better. So even though individual taxis are taking a longer route to get to the airport, as a whole, everyone is hopefully more likely to make their flight. So this, I hope you can understand how this would have a direct impact on our lives, because we're all hate being stuck in traffic. So maybe this is something that could help. But this also applies to any kind of optimization problem, be it traffic flow, routing, scheduling, anything like that is basically the same type of problem. And the quantum computer is actually quite good at solving these. Okay, so today I've talked a little bit about the transistor computer and how we're reaching the end of that era. And if we want to solve harder problems, which I really think we do, we need to look to a new paradigm for computation. I've told you a little bit about quantum mechanics and some of the weird things that comes out of that, specifically this superposition state, entanglement, and quantum tunneling, and how that might help us speed up computation in a quantum processor. While I want to emphasize that the current quantum processors that we have available today are not yet clearly outperforming the best classical resources that we have available, we're kind of on the cusp. We're starting to get there. We're starting to see that we can solve some real-world applications. And while I don't think that quantum computers are going to be in our phones in the next few years, sorry, I do think that it will have a very profound impact on our lives, whether we're aware of it or not. Thank you.